Today we are going to discuss about the counters. Counter is a circuit which consists of several flip-flops and is used to count the number of clock pulses that we apply at the clock input. Now, at any instant, the output of this counters will be a binary value which is equal to the number of clock pulses that we apply. Now, based on the how the clock signal is applied, we can classify the counters as asynchronous counter and synchronous counter. Now in this video we are going to concentrate on asynchronous counter, which is also known as the ripple counters. Now in this counter, all the flip-flops which is used to construct the counters are not clocked simultaneously. That is why the name asynchronous. So we will be applying the clock pulse only to the first flip-flop, that is the flip-flop which shows the lowest bit, LSB bit, and all other flip-flops are triggered by using the output of the previous stage flip-flop. As an example, we can take a 4-bit synchronous counter. So when we discuss the flip-flops, we've seen that using a single flip-flop, we can store 1 bit of data. So if you want to construct a counter with a 4-bit, which can count up to 4 bits, you need minimum 4 flip-flops. That means if you want to construct a n-bit counter, you require n flip-flops. So here we are using a 4-bit asynchronous counter. That means you require 4 flip-flops. And again, in the title, you can see that it is an up. It is mentioned as up counter. Up counting means it is counting from 0, 0, 0, 0 to 1, 1, 1, 1. That is why the name up counting. That is, the counting is in the ascending order. Now, similarly, you can obtain the down counter, which can count from 1, 1, 1, 1 to 0, 0, the descending order. Okay. Now we can see the circuit diagram for the 4-bit asynchronous counter. Now here the slide, the circuit diagram is shown. Here you can see that we are using 4 flip-flop A, B, C, D, and all the flip-flops use .jk flip-flop, and we are connecting the external clock pulse only to the first flip-flop, that is flip-flop A, and all other flip-flops B, C, D are triggered from the output of the previous flip-flop. And here all the JK terminals of the flip-flops are connected to a plus VDD, which is the high state. That means we are making our flip-flop as JK as 1, 1. When J and K is 1, the JK flip-flop output is Q and complement. That means whatever be the previous state, its complement will be the next state. And if you check the flip-flops, it is all the flip-flops are negative edge triggered flip-flops. That means the triggering occurs when your clock pulse is jumping from 1 to 0. That is, when you apply a clock pulse like this, the triggering occurs when there is a negative edge is occurring. That means during the change from 1 to 0, your output will change. Okay. Initially, we are applying a trigger reset signal so that all the outputs of your flip-flops are made as 0. So first output combination is 0, 0, 0, 0. Now in the next step, we are giving a clock pulse when the negative edge of the clock pulse comes. That means when the clock pulse is changing from 1 to 0, your output of your A flip-flop will change from 0 to 1, because the previous state was 0. It will get toggled and it will become 1. Now the output of B, C and D these three flip-flops will not change, because there is no clock pulse that is coming from the previous state which changed from 1 to 0. Here you can see that it is changing from 0 to 1. Here there is no change, it is 0 itself. This is again no change, 0 itself, and here also no change, 0 itself. So the next step, when the first clock pulse comes, the output will become 0, 0, 0, 1. So now the output is 0, 0, 0, 1. Now we will apply the next clock pulse, and when the next clock pulse is applied, when the next clock pulse comes, the negative edge of the next clock, that is here we will be applying the clock. So when the next clock comes, the flip-flop A will change its state from 1 to 0. So here the change is occurring from 1 to 0. That means it is a negative going edge. So the flip-flop B will also get triggered. It changes its state from 0 to 1. So the output of B, it is changing from 0 to 1, which act as the clock pulse for the C flip-flop. Now it is changing from 0 to 1. So there is no triggering occurring. So it will be again remains as 0 itself. And there is no change for the D flip-flop also. So we will get the next state as 0, 0, 1, 0. Now similarly, when we apply the next clock pulse, that is when the clock pulse is changing from, again next clock pulse comes and it is changing from 1 to 0, flip-flop A get again triggered and it will change from 0 to 1. Now it is changing from 0 to 1, so it is a positive edge. So your flip-flop V will not get triggered, so it will remains as 1 itself. Now it is the B output is changing from 1 to 1, so there is no triggering for C flip-flop or D flip-flop. So the output will be remaining as 0 and here as 0. So the next state will be 0, 0, 1, 1. Now we can check the one more state, that is when next clock pulse comes. That is again when your input is changing from 1 to 0. Again the flip-flop A get triggered, so it will change from 1 to 0. Your output of flip-flop A will be changing from 1 to 0. So this 1 to 0 change will act as a trigger signal for the flip-flop B. So your flip-flop B will get changed as 0. So again you can see that here also the output of the flip-flop B also changing from 1 to 0. That is a negative edge. That will act as the trigger signal for the C flip-flop. So C flip-flop out will also get triggered. That is, it changed from 0 to 1. So here the C flip-flop output is changing from 0 to 1. That means that is a positive going edge. So there will not be any change for the D flip-flop. So the output of the D flip-flop will remains as 0. So the current state will be 0, 1, 0, 0. So that is the output of your 4-bit asynchronous flip-flop. So this is the state when the fourth clock pulse is coming. Similarly, when next clock pulse also coming, you can find out the changes for each flip-flops. Now we can just see the truth table for this asynchronous counter, that is so state and each state you can see that stage is changing from 0, 0, 0, 0 to 1, 1, 1, 1. In this slide we are going to discuss the timing diagram for 4-bit asynchronous up count that we discussed. That is here you can see that the first one it is the clock signal, and this is the output of first flip-flop, that is flip-flop A. Then this is the flip-flop B output, this is flip-flop C output, and this is the flip-flop D output. So before applying the first clock pulse, that is before coming the next first clock pulse, we are making all the output as 0. This is made as 0, and this is made as 0, and this is made as 0 using a reset pin. Now here, when the first clock pulse, that is when the first negative edge occurs, your QA will be changing from 0 to 1. So QA is acting as the clock pulse for QB, that is the B flip-flop. So here the clock pulse for the B, it is changing from 0 to 1. We know that all the flip-flops are negative edge triggered. So here you will get a positive edge because this is a clock pulse for the B flip-flop. So there will not be any change. Similarly, QC and QD, there is no change because there is no negative edge coming for the previous output state. Now when the next clock pulse comes, that is the second clock pulse comes, here I can see that QA changed from 1 to 0. QA is changing from 1 to 0. This QA act as the clock pulse for the B flip-flop. Now here it is the negative edge 1 to 0 change, so your QB will be changing from 0 to 1. So QB is changing from 0 to 1. This acts as the clock pulse for the QZ, but it is a positive edge, so there is no triggering, so it will remain as 0. And similarly QD also remains as 0. Now similarly next clock pulse comes, here you can see that QA change from 0 to 1. Since the change is 0 to 1, QB will not change, it will remain as 1. And similarly QZ and QD also. When the next clock pulse comes, that is your QA will change from 1 to 0. So there is a negative edge. So your QB will change from 1 to 0. Initial previous state was 1, so it will get toggled to 0. Now there also there is a negative edge that acts as the clock pulse for the C flip-flop. So C flip-flop also get triggered, so it will change from 0 to 1. Since the here C flip-flop output is changing from 0 to 1, that is act as a clock pulse for the D flip-flop, but that is a positive edge, so there is not triggering occurring for the D flip-flop. So from this I can see that when you are applying the clock pulse directly to the A flip-flop, so since the stage that is JK terminal we are connecting to 1 1, whenever the negative clock pulse comes for the when we apply the terminal of flip-flop A, it will get toggled. So it will get toggled for each clock pulse that we apply. Now QB will be changing its state, or it will get toggled when there is a negative edge that is coming for QA. So whenever QA become or QA change from 1 to 0, that is negative edge, your QB will be changing. So here there is a 1 to 0 change, here that is the next 1 to 0, here that is the next one, here that is next one, here this next one. Similarly, the QC will change its state only when there is a negative edge coming for the QB output. So here you can see that the QB output is changing at this state, so your output QC will be changing from 0 to 1. Next state, that is next 1 to 0 change for the QB occur at this point. The QC will change from 1 to 0. Similarly, for the D flip-flop to change, that is flip-flop D to change, there should be a negative edge at the QZ terminal. So here you can see that the negative occurs only at this point. So there the output of QD change from 0 to 1. So this is the timing diagram for the for-bit asynchronous up counter. So here you can see that the first state coming is 0 0 0, then 0 0 1 0 0 1, then 0 0 1 0, 0 0 1 1, then up to it is counting up to 1 1 1 1. Now when it is 1 1 1 1, the next state, here you can see that when next pulse is coming, it will change from 1 to 0. So that is the negative edge for the QB, so it will change from 1 to 0. That will be negative edge for the QZ, so it will change its state. Here it is 1, so it will change 1 to 0. Then that will act as a negative pulse to the next flip-flop, that is flip-flop D. So there also will be getting a trigger signal. So all the state of your flip-flop get changed from 0 0 1 1 1 1 to 0 0 0 0. So that is the next state. So this states will continue. So when you apply the next clock pulse, your output will change from 0 0 0 0 to 0 0 0 1. So this continues. Next is one of the term associated with this counter, that is known as the modulus of a counter. Actually, it indicates the number of states that present for the counter. Now, if you are taking the 4-bit asynchronous counter, it has 16 different states. So you can say that 4-bit asynchronous counter, it is a mode 16 ripple counter or a mode 16 asynchronous counter. Mode and its number, it will indicate the number of states that is present for that particular counter. Next is how we will construct a mode n counter. That is, we discussed that a 16-bit counter you can construct using A4 flip-flops. Similarly, you can construct if you are using 3 flip-flops, you can construct a 8-bit counter. Now, suppose if you want a mode 10, that is 10 output states 0 to 9, if you want to count how will you construct that counter, and what is the procedure for that one. So before going to that, there is some basic thing that we already discussed. The that is, for a flip-flop, there are two pins called clear and preset. This clear, when you apply a lower signal to the clear pin of a flip-flop, whatever be the input state, your output of flip-flop get reset. That means Q output will get to 0. Similarly, if you apply a preset signal to the flip-flop, whatever be the input combination, the output will be 1. So these two pins we usually use for constructing the different circuit using the flip-flop. So here in this mode N counter, we will be using this clear pin to clear or to reset your flip-flop stage to 0, 0. Now we can see if you want to construct a, suppose if you want to construct a mode 10 counter. So how will you decide how many flip-flops you require? So that is important criteria, the first thing you have to decide. So suppose this is a mode 10 counter. We know that if you are using 2 flip-flop, you can construct 2 raised to 2, that is a 4-state counter. That means you can construct a mode 4 counter. If you are using 3 flip-flop, you can construct a counter with 8 state. Similarly, if you want if you can use 4 flip-flop, you can construct a 16 state or mode 16 counter. Now from this, if you have n flip-flop, you can construct a 2 raised to n, that is 2 raised to n state counter. Okay, now here we need a mode 10 counter. That means we need a 10 state output. So if you are using 3 flip-flop, we can obtain only 8 state. If you are using 4 flip-flop, you can get a 16 state. So you have to select a 4 flip-flop counter. That means if you want to construct a mode 10 counter, you have to use minimum 4 flip-flop. Similarly, if you want to construct a mode 6, if you want to construct a mode 6, if you are using 2 flip-flop, you can get a 4 state. But for mode 6 means you are having a 6 state. So you cannot obtain a 6 state counter using 2 flip-flops. If you are using 3 flip-flop, you can get 8 state. So you have to use minimum 3 flip-flops in order to get a mode 6 counter. So to construct a mode N counter, first you have to find the number of flip-flops required. So if you are using n flip-flop, suppose if you want to construct a mode N counter, you have to choose a number of flip-flops based on the number of state required. So here there is a equation shown, that is there is a relation 2 raised to n minus 1 less than equal to capital N less than equal to 2 raised to n, where n is the number of flip-flops and capital N is the number of state you require. So you have to conduct all the flip-flops as a ripple counter, just like that we discussed. You have to connect all the flip-flops as a ripple counter. That means you will be applying the clock pulse only to the LSB. Then the LSB output is taken and it is given as the clock pulse for the next flip-flop, and this process continues. And you have to find out the state of each flip-flops where it becomes 1 when your state n occur. That means when the 9th, suppose if you want to construct a mode 10 counter, when the state 10, that is the 10th state is coming, what are the whichever flip-flop is becoming 1, that you have to connect to a NAND gate, and this NAND gate output is connected to the clear input of the each flip-flops. That is we are doing to ensure that after 10th state you have to go to the
0. That means if you are constructing a mode 10 counter, means it will be counting from 0 0 0 0 to 0 1 sorry 1 0 1 0. So when the 10th state occur, it will the next state of your counter is 0 0 0. So when this state occur, the next state should be 0 0 0 0. In ripple counter, if this state occurs 1 0 1 0 occur, the next state is 1 0 1 1. So when this state is coming, it should automatically change to 0 0 0 0. That for that purpose we are using this NAND gate. So the output of the NAND gate is given to the clear input, because clear's input, it is a low signal triggered terminal. And when the low signal is applied to the clear pin, all the flip-flops output get reset. That means all the state become 0. To make the clear the construction of mode n counter, we can take one example as mode 10 counter, which is also known as the decade counter. It will count from 0 to 9, that is total 0 to 9, that is total 10 state will be there. So first we have to find out how many flip-flops you have to use, the number of flip-flops required. So here n is equal to 10. So if you can use the relation that we discussed in the previous slide, if you are using a 4 flip-flop, you will get 16 state. If you are using 3 flip-flop, you will get only 8 state. So we need a 10 state. So 10 state means it is greater than 8. So we have to use the next higher state flip-flops. That means you have to use minimum 4 flip-flops in order to construct the mode 10 counter. So it is given as 2 raised to 1, means we will get only 2 state, 2 flip-flop, 4 state, 3 flip-flop, 8 state, 4 flip-flop, 16 state, which is greater than 10. Okay, so we need a counter with 4 flip-flops. It is not 3, it is 4 flip-flops. Now if you are using a 4 flip-flops counter, we know that it will be counting from 0 0 to 1 1 1 1. It is 0 to 15 in decimal. So you have to ensure that when the 10th state is occurring, the next state should be 0 0 0 0. That we ensure with the help of a NAND gate. So here this is the circuit for the mode 16 counter that we discussed already. Here you can see that we are connecting the external clock pulse to the first flip-flop, and all other flip-flops are triggered from the previous state output. So if you are connecting 4 flip-flops like this, it will count from 0 0 0 0 to 1 1 1 1. That means you will get 16 state, but we need only 10 state. So in order to obtain that 10 state counter, we have to find out a way to reset all the flip-flops when the 10th state is okay. When the 10th state is changing. So if you are using a mode 16 counter, the state will be changing from 0 0 0 0 to 1 1 1. So the next state will be 0 0 0 1. 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 1 1 1 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 1 1 1. So these are the states of a mode 16 counter. So this will be QD, this will be QC, this will be QB, and this will be QA. Now for a mode 10 counter, we need 0 1 2. If you write the decimal number, this 5 6 7 8 9, this 10 11 12 13 14 and 15. So if you are using a mode 16 counter, it will count from 0 to 15. But for mode 10 counter, we need a state from 0 to 9. So we need only states from 0 to 9, right? That means when the 10th state, that is when this state is coming, you have to reset your flip-flop so that your output will become again 0 0 0 0. Now how will you make that? So you have here, you can see that when the 10th state is occurring, you can see that QD is high and QB is high. That is, when the 10th state is occurring, we need only from 0 to 9. That is, when the decimal number is 10, that is 11th. When the decimal number is 10, that is 11th state. 10th state is 1001. 11th state is 1010. So you need up to this. So when the 11th state occurs, that is 1010 occur, it should automatically change to 0000. So if you check, you can see that at this stage, when the 11th state occur, QD and QB is high. So what we will do is, we will make these two, or we will connect these two input to a NAND gate. That is, we will connect QD and QB to a NAND gate. So for all other states, you can see that QD and this QB never become equal to 1. So when the 11th state occur, that is when QD and QB equal to 1, the output of this NAND gate will be 0. For all other states that occur before, your output will be 1. So this we will connect to the reset pin of your all the flip-flops. So when QD is equal to 1 and QB is equal to 1, that is when the 11th state is occurring, your output will become 1 and output will become 0 and all the flip-flops get reset. So the circuit diagram for mode 10 counter is shown in the slide. Here I can see that we are connecting the output of QD and QB to a NAND gate, and this NAND gate output is fed to the clear pin of all the flip-flops. So here you can see that here we are feeding as QB and here we are feeding as QD. So QB and QD is becoming 1 in this case only when the next, that is 11th state is occurring. That is when the decimal number equal to 10 is occurring. This will be QB and QD will be 1. Then at that time this NAND gate output is becoming 0 and all the clear pin become low. So the output of each and every flip-flop will become equal to 0. That is how we are designing mode 10 counter. Now the truth table for the mode 10 counter is shown in the slide. Here you can see that it is counting from 000 up to 1001. When the 10th state, when the 11th state is occurring, that is 1011 is occurring, all the flip-flop is getting reset and your output state will become 0000. Now when the next clock pulse comes, again the sequence will repeat. The timing diagram for mode 10 counter is shown in the slide. Here you can see that the counter is starting from 00 as your 4-bit ripple counter, and when the clock pulse comes, it will change from 000 to 001, and this process continues, and when in this instant it becoming 1001, that is the binary equal to 9. Now when the next state comes, that is when the next clock pulse comes, this 1 is getting changed to 0. and this since there is a negative clock going negative edge is coming here, your QB will be changing from 0 to 1, and QC there is no change, it will remains as 0, whereas again QD is again remains as 1. Now you can see that your QD and QB is 1 at this instant. So what happens to the NAND gate output? NAND gate output will become 0. Initially it was 1. For all other input it will be 1. At this instant the NAND gate output will become 0. So when the NAND gate output is 0 means a 0 signal will be coming to the clear pin of all the flip-flops. That means your flip-flop get reset. So flip-flop gets reset means your this flip-flop output will become 0. Here it is again remains as 0. This will become 0 and this will become 0. So the state will become 0 0 0 0. When it is 0 0 0, again your NAND gate output will become 1, and this will be 1 till the next 1001 comes. So again it will start from 0 0 0 and the next state will be 0 0 0 1, and this continues. So this is the timing diagram for this mode 10 counter. Here you can see that for a small instant of time the output will be 1 0 1 0 till the your NAND gate is changing from 1 to 0. Your output will be 1 0 1 0. So that delay, that is for the propagation delay of your NAND gate, your output of counter will be 1 0 1 0, but it will be very small, so it may not be a visible one.